Assalamu alaikum students. So now we are going to revise some of our key concepts that was related to our Bernoulli equation. We get different type of pressure: static pressure, dynamic pressure, stagnation pressure, total pressure from the Bernoulli equation. That's what we are going to discuss now. And what are the applications of Bernoulli equation? That's what we are going to go through again. And the flow rate measurement devices, and finally the energy and the hydraulic grade lines. So let's move on to our presentation. Now this is Bernoulli equation. Bernoulli equation is same as the Newton's second law of motion for rigid body. You can also say that the Bernoulli equation is the equation of motion for fluids. You can say that because we have derived the Bernoulli equation, as you remember, by using the second law of motion and integrating this for a fluid particle along the streamline. So we derived the Bernoulli equation by using this equation, the equation of motion. So what we got the equation of motion for fluids. Normally this equation is used for rigid bodies, for solid rigid bodies, but Bernoulli equation is used for fluid. It is the equation of motion of fluids. So what does this equation say? This equation says that the pressure energy plus the kinetic energy plus the potential energy is equal to constant. What does this mean? This means that the change in kinetic energy results from change in pressure energy and the change in potential energy. So the change in pressure energy and the change in potential energy results in a change of kinetic energy. So physically, if we change the pressure energy of a fluid and the potential energy of a fluid, so the fluid will either move or it will comes to a stop. So this is what the Bernoulli equation is telling us, that either by changing the pressure or by changing the potential energy of the fluid, we can increase and decrease the kinetic energy of the fluid. So either we can move the fluid or we can bring it to a stop. So it can also be defined, this Bernoulli equation, by this statement that the work done on a particle by all forces acting on the particle is equal to the change of kinetic energy of the particle. So here they are talking about forces. So what are these forces? These are the pressure forces. The pressure forces, the forces that are occurring due to pressure, and these are the forces that are occurring due to gravity. So by changing these two forces, we can change the motion of the fluid, and as you can see, this motion is represented by the kinetic energy term. So this change, overall this change will be constant along the streamline. It means that if we have a streamline like this, we take 2 points, one is 0.1 and the other is 0.2, and we apply this Bernoulli equation for 0.1 P1 plus half rho V1 square plus gamma Z1, and similarly for this point P2 plus half rho V2 square plus gamma Z2. So what is going to happen, that any change in the pressure here will result in a change in kinetic energy, or any change in the potential energy of the fluid here will result in the change in kinetic energy. So if these quantities change from one point to the another point, overall the result will be the same on the right hand side of this equation. So overall this P1 plus half rho V1 square plus gamma Z1 will be equal to this whole P2 plus half rho V2 square plus gamma Z2. So this is what the Bernoulli equation states, and this is what the conservation of from where we get the conservation of energy also. So this also satisfies the conservation of energy statement. So overall Bernoulli equation is the equation of motion for fluids, and fluids move by either change in the pressure energy or the change in the potential energy or of the fluid, or if we talk in terms of forces, so due to change in pressure forces and gravity forces, we can change the kinetic energy of the fluid. So in short, this is what the Bernoulli equation states. So now let's move forward and look at some of the pressures that results when we make a fluid stop. So when a fluid is moving and we make it stop, so three type of pressures occur, that is the static pressure, dynamic pressure, and the stagnation pressure. And these pressures occur when a moving fluid is brought to rest. These pressures will be explained with the help of a diagram in the next slide. So this was the Bernoulli equation, and again in short, Bernoulli equation is the equation of motion for the fluid. So now moving on to the next slide to explain what are the static pressures, what is a dynamic pressure, and what is a stagnation pressure. So this is what we are going to use this figure to explain static pressure, dynamic pressure, and total pressure or stagnation pressure. So if we have a fluid that is moving through a pipe, this is fluid entering the pipe, as you can see, having a certain velocity, and what we are going to do first is to drill a hole here at point 3. At point 3 we drill a hole and we attach this piezometer tube here. This is a piezometer tube, and piezometer tube, as you remember, is used to measure the static pressure. So how are we going to do that is we are going to take height from the center of this pipe up to 0.4. When we attach a piezometer tube, this piezometer tube to at this 0.3 by drilling a hole here, the liquid will rise to a certain point 4. This rise in liquid up to a certain point 4 is due to the static pressure of this fluid. Means if you consider that there is no hole at this point 3, so this liquid will be applying some pressure at the walls of this pipe. So how can we measure this pressure? By simply drilling a hole and attaching a piezometer tube here. So we have drilled a hole here and attached a piezometer tube. So this rise in fluid up to 0.4 is now my static pressure from point 1 up to 0.4. So this is the static pressure that I am talking about. Now for my dynamic pressure, what I am going to use is I am going to use this pitot tube. This is the pitot tube, or pitostatic tube as they call this. So when I place this pitot tube in the stream, in the flow stream, remember that the fluid is still flowing here. So when I place this pitot tube upstream to this flow, means that its inlet is upstream to this flow. This is the inlet of this pitostatic tube. This is the inlet, and then this inlet is upstream to this fluid flowing, means it is facing this flow directly. So what will happen due to the velocity of the fluid, there will be first there will be some disturbance here, some eddies will be created, there will be some disturbance, but once the fluid normalizes, the fluid will again rise in this tube up to a certain height. This height is due to the velocity of the fluid. This height is attained due to the velocity of the fluid. This height is attained by the fluid velocity, because the fluid has a certain velocity. So if we insert a pitostatic tube in this stream, so the fluid will rise in this tube, and the height of this fluid will be governed by the velocity of this fluid. So now we have a point 2 here at the inlet of this pitostatic tube, and this point at this point, or if we take a point here, let's say we have a point, let's say I say this is 0.5. So at point 2 and 0.5, the velocity will be 0. So it means the fluid is at rest from point 2 to point 5. The fluid will be at rest. So this will be my total pressure, because here the fluid is brought to rest. So by bringing a fluid to rest, the fluid will exert a certain amount of force. If you can imagine that, let's suppose a fluid is flowing, and by bringing this fluid to a stop, we say that we have installed a barrier here. So what will this fluid do? It will apply a certain amount of force, and that force is the pressure force. That is it is applying, and then it will come to a rest. So after applying a certain amount of pressure force, this fluid will come to rest. So this is what it is happening here, that here the fluid is at rest, but it has applied a certain amount of pressure force, and that pressure force is the total pressure force. So now if we apply the Bernoulli equation on point 1 and on point 2, so what we are going to get is, that is the two equation, that is the P1 plus half rho V1 square plus gamma Z1 is equal to P2 plus half rho V2 square plus gamma Z2. So what is happening here, that point 1 and point 2 are at the same height. So we will cancel out these terms. This term will be cancelled out. This term will be cancelled out. At point 1, there will be a certain amount of pressure, that is the static pressure, that is measured up to this point 4. From point 1 to 4, this will be the static pressure that we are going to measure. And the velocity at point 1, there will be a certain amount of velocity. At point 2, the fluid is at rest, so at V2 the velocity will be 0. So this term will be neglected. So what we are going to get is an equation that is in this form, and that is equal to P2 is equal to P1 plus half rho V square. So what does this equation mean? This equation shows us the different type of pressure. So P2 is the point 2 is the point where the fluid is at rest. So here the pressure will be the total pressure. This pressure is also called stagnation pressure. So this total pressure is equal to the P1. So at point 1, we have measured static pressure. So P1 is the static pressure plus half rho V square, that is the dynamic pressure. That is the pressure due to the velocity of the fluid. So by using this setup and applying Bernoulli equation on point 1 and point 2, we have come up with certain terms of pressure, that is the total pressure is equal to the static pressure plus dynamic pressure. So as you can see, the total pressure is at point 2 where the fluid is at rest, and by bringing fluid at rest requires a certain amount of force that the fluid will apply on that surface. So here we have used a pitot static tube for that purpose, and again in this tube overall the fluid is at rest. This whole fluid is at rest. So at point 2 the fluid will be at rest. So at point 2 we have the total pressure that resulted when we brought the fluid of a certain velocity at rest at this point 2. And at point 1 we measured the static pressure by using this piezometer tube. So by using this piezometer tube we measured the static pressure at point 1 up to point 4. So this was the static pressure, and by applying this Bernoulli equation on point 1, point 2, we got this equation in which we said that the static total pressure is equal to the static pressure plus the dynamic pressure. So by using Bernoulli equation in this setup, we have come up with different pressure terms. So where is this formula used? This formula is used to measure the velocity of aircraft, and this is the formula for a pitot-static tube. So now moving on to the next slide, where we are going to see the application of this formula in a pitot-static tube. So what is a pitot-static tube used for? It is used to measure velocity of an aircraft, and it uses the same formula in which the total pressure is equal to the static pressure plus dynamic pressure. So we have already derived this formula, that how the total pressure becomes equal to the static pressure plus the dynamic pressure. What we are going to see is a pitot-static tube. This is a diagram of a pitot-static tube. This is where the velocity, the air, this is the inlet, sorry, this is the point 2 is the inlet. Okay, point 2 is the inlet. Point 1 is a hole that is used for to, if any of the air condenses inside here, so this hole is used to get rid of the condensed air, or if any water enters this pitot-static tube. So point 1 is used to get rid of water if it enters this stream. So what happens is the air enters here, and then we have two ports. One is this port point 4 and the other is at point 3. So the air moves up to point 4 and up to point 3, and at point 4 we measure the static pressure. We measure the static pressure, and at point 3 we measure the total pressure, P total. So how do we do that? How do we measure the static pressure, and how do we measure the total or the stagnation pressure? So what we do, we install a manometer to these ports. We installed a manometer to these ports, and inside this manometer we have a certain amount of gauge fluid, and by the difference of this height h that we are going to get from this gauge fluid, we can measure the pressure difference, that is P3 minus P4 will be equal to gamma and h. Okay, this is the h. So by measuring this pressure difference, we can actually use this to find the velocity of the fluid. So again, point 3, at point 3, this is the total pressure. This is the total pressure. As you can see, why this is the total pressure, because this surface, this control surface is facing the upstream fluid, and this is the, just like in the previous slide, like we drilled a hole to see the static pressure of the fluid. So this is the hole that we drilled and attached a piezometer tube, and here we again is looking at the upstream fluid. So this is what we are doing. We are using a pitot-static tube, and we have installed a manometer to it to measure this static and total pressure, and by taking the difference of the total and the static pressure, we can use it to measure the velocity by actually applying the Bernoulli equation at point 3 and point 4. So by applying this equation, this is what we are going to get. P3 is equal to P4 plus half rho v square. This is the total pressure is equal to the static pressure plus the dynamic pressure. So this is the formula that we already derived, and by taking the difference of the total and the static pressure, we get the dynamic pressure, and by knowing the value of this P3 minus P4 from here, we can actually now compute the velocity of our aircraft. So this is what the application of pitot-static tube here, and pitot-static tube utilizes the concept of total pressure, static pressure, dynamic pressure to actually measure the velocity of an aircraft. So this will be the formula that is used to measure the velocity of this flow of in this case the aircraft. This will be the formula to measure the velocity of the aircraft. So this is actually by taking the concepts of total pressure, dynamic pressure and static pressure from the Bernoulli equation, applying it on pitot-static tube, using manometer to take the pressure difference in terms of height, and then use it in the formula in which the total pressure is equal to static pressure plus dynamic pressure, we can actually compute the velocity of an aircraft. Now we are going to see some applications of the Bernoulli equation, and the first application that we get from the Bernoulli equation is measuring the velocity of a free jet. So what is a free jet? A free jet is created when there is a small opening in a large reservoir that goes to the atmosphere. It means that if we have a large reservoir and there is a small opening at the bottom here, so this is what we are going to get. A form of jet will be created if we draw it like this. A form of jet will be created when this opening is right here is opened. If this valve is open, so what we are going to get? We are going to get a jet of fluid. A jet of fluid. So by taking 2 points, one here and the other here, and applying Bernoulli equations on those 2 points, we can actually compute the formula for this jet, which will come out to be under root 2gh. So how does this come out to be under root 2gh? Let's see this. Apply Bernoulli equation properly. And so this is our free jet situation in which a small opening, this is a small opening here, and through this small opening a jet of fluid is exiting, and this is the reservoir, a large reservoir. So what we have done is we have taken 2 points, point 1 and point 2, and now we are going to write the formula, Bernoulli equation for this point 1 and point 2, and this is what we get. First, this is what we have done by writing formula for point 1 and point 2. Now at both point 1 and point 2 the pressure is atmospheric pressure, so that pressure can be ignored. The velocity at point 1 is 0 when we compare it to velocity at point 2. So velocity at point 2 is very high than the velocity at point 1. So in this case the velocity at point 1 is considered to be 0 because it is very less compared to velocity at point 2. We are going to velocity at point 2 is equal to v. If we take our point 2 as our reference point, so from this reference point up until point 1, what we are going to get is the height of h. So z1 will be equal to h, and z2 is the reference point, so that will be equal to 0. Putting all these values in this equation gives us the formula of v is equal to under root 2gh. So this is the formula that is used to find the velocity of free jets. And this is the same formula when we want to find the velocity of something rigid falling, free fall in our atmosphere. So if this is a rigid body for free falling in our atmosphere, so this same velocity v is equal to under root 2gh is used to find the velocity of a free falling object. So this is the first application of the Bernoulli equation by using it to find the velocity of free jet. What happens when a jet of small fluid exit a hole is the vena contracta effect. So what is the vena contracta effect? If we can see with the help of this diagram that was used in your Munson book, the jet velocity, that is the water jet that is exiting this reservoir, the jet diameter is less than the diameter of this hole. So it contracts, the jet contracts when it exits a hole. So this is called the vena contracta effect. So this effect occurs due to the different hole shapes. So this is a knife edge. So in a knife edge, vena contracta effect occurs, the hole diameter is more than the jet diameter. Here in a well-rounded hole, the jet diameter and the hole diameter are same, and in case of sharp edge, this jet diameter is again decreased and the hole diameter is greater than the jet diameter. And here again in the reentrant type of hole, we get the jet diameter less than the diameter of the hole. So we have a formula through which we can compute these values of contractor effect, Wiener contractor effect, and that formula is the contraction coefficient that can be used to see the Wiener contractor effect in a jet flow situation. So here, as you can see, the Wiener contractor CC coefficient is 1 because the jet diameter and the hole diameter are the same. Whenever this ratio is less than 1, so it means that the Wiener contractor effect is occurring and the jet diameter is less than the hole diameter. So this is a sort of phenomena that occurs when a jet flows. Next up is the confined flow. Confined flows are those flows in which the fluid is not exposed to the atmosphere. It throughout moves in a confined pipe, means it is a closed channel and the fluid is circulating inside that closed channel. So depending on the geometry of the channel, the fluid velocity and pressure might change. So to compute the velocity and the pressure change, we use again the same Bernoulli equation. This is a closed channel. So here you can see that due to the change in the cross section of that channel, means the channel is converging. So the velocity of this fluid inside this channel will increase when it flows from point 1 to point 2. So to compute this velocity change, or to as the velocity increases, the pressure will decrease. So to compute changes in velocity or the changes in pressure in the confined flow, we again use the Bernoulli equation. So again, confined flows, this statement define what are the confined flows. You can read it yourself. And such cases include nozzle pipes of variable diameter for which fluid velocity changes, as we already discussed, that this fluid velocity changes due to the cross section of this confined geometry. So for this situation, it is necessary to use the conservation of mass continuity equation along with the Bernoulli equation. So we use Bernoulli equation plus the conservation of mass principle, that is continuity equation basically, to compute this change. So what we are going to do is we are going to take these 2 points, that is point 1 and point 2, and we are going to apply this volumetric flow rate and this mass flow rate equation on point 1 and point 2. So by applying these two equations, what we are going to get is we get the continuity equation, that is A1 V1 is equal to A2 V2. So a change in area at point 1 will give us the velocity at point 1, or a change in area at point 2 will give us velocity at point 2. So with the help of this equation, we are now incorporating the change in the geometry of our pipe. So by changing the geometry of the pipe, we get changes in pressure and velocities, and that change in pressure and velocities can be computed by using this continuity equation. As you remember, we derived this continuity equation by using the Reynolds transport theorem. So now you know how this continuity equation got there and how it can be applied to this simple flow situation. Next up is the flow rate measurement, and the flow rate measurement is used both in confined channels and in open channels. So first we are going to look at the methods that are used to measure the flow rate inside a pipe. So if we have a pipe, so this can have 3 arrangements. The one arrangement is that of an orifice, that is the orifice. The second arrangement is that of a nozzle, and the third arrangement is that of a venturi. So these 3 arrangements can be used to measure the flow rate inside the pipe. So what we are going to do is, we have already taken 2 sections, that is section 1 and section 2. One is one is upstream to this orifice and one is downstream to this orifice. Again, there is a section here upstream to this nozzle and downstream to this nozzle. We have a section here upstream to this venturi and downstream to this venturi. So that's what we are going to do. We are going to take these 2 sections and apply Bernoulli equation to these 2 sections and apply and by applying Bernoulli equation, what we are going to get is the formula for the flow rates for these orifice, nozzle and venturi. So by applying equation 1, that is our equation 1, that is the Bernoulli equation at section 1 and section 2, the gamma z term is excluded here because these 2 sections will be considered to be at the same height or the height difference will be considered to be negligible. So what we are considering is this equation for both these sections for these three arrangements, and what we are going to get is this by combining this equation 1 with continuity equation, that is a1 v1 is equal to a2 v2. What we are going to get is an equation for our flow rate for orifice, nozzle and venturi. I'm going to repeat this again. This is the equation that is going to be used for all these three arrangements. Not a single one, but this equation can be used by these three arrangements, for these three arrangements, and to measure the flow rate inside the pipe. So now moving on to the part where we measure flows in open channels. So flow rate measurement in open channels like your rivers, your canals, your barrages can be done by using the Bernoulli equation. So these Bernoulli equations are used to measure flow rates in open channels such as flumes and irrigation ditches. The two flow rate devices that we are going to discuss is the first one is the sluice gate, and the other is the weir. So sluice gate and weir is used to measure flow rate in open channels. These are not the only two devices that are used. Other devices are also used, but most commonly sluice gate and weir is used to measure the flow rate in open channel. So let's look at the sluice gate. This is the sluice gate, and what happens in a sluice gate is this gate, this is the sluice gate, and through this gate at the bottom a fluid flows. When the fluid flow, so what we do is we get 2 points. One is point 1 and one is point 2. By applying Bernoulli equation to these 2 points, we get a equation for our flow rate in open channel for this sluice gate. So let's see how we derive this equation. This is the actual diagram of a sluice gate, and this is the schematic diagram. So if this is again the sluice gate, so what we are going to do is to use these equation again in tandem, that is the Bernoulli equation and the continuity equation in tandem to derive this equation, that is the equation that is used to measure the flow rate through a sluice gate. So here the terms are pretty clear. The area is taken as BZ1 and area at 2 is taken as BZ2. So B is the width of this gate, the sluice gate, and to define the area we need to multiply this width by the total height. So in this case the total height for area A1 will be, for area at A1 will be BZ1, and for area at point 2 will be the width of this gate and this height Z2. So this is what we are going to get, these areas, and by putting it into the continuity equation and then combining it with this equation, what we get is the equation 3.21 for the flow rate that is used to measure the flow through this sluice gate. And we can neglect this term in the denominator of this equation. If our height is too much, then the width of the fluid that is exiting at this point 1. So we can ignore this term in the denominator of this equation and write our flow rate equation for the sluice gate like this. So now moving on to our weir. So this is our weir. Weir is also a plate that is installed in the channel, and then with the help of these dimensions of this plate and the dimensions of the fluid that is passing this plate, we can measure our flow rate. So this is the flow rate equation. C1 is a constant, and this constant is determined by the shape of this weir, and this is the height of the fluid above this plate. From this point to this point, this is the height of the fluid above this plate. This is the width of the plate, and again this is again this height, and these equations are combined to get the equation of the flow rate for the weir. So this is the equation for the flow rate of weir. So these are the sluice gate and weir are used to uh, calculate the flow rate of fluid, that is water in this case, to calculate the flow rate of water in open channels. So now moving on to our next topic. This is our next topic, that is the energy line and the hydraulic grade line. So what does the energy line and the hydraulic grade line represent? The energy grade line and the hydraulic grade line are actual graphical representation of our Bernoulli equation. So if you remember from our Bernoulli equation, what do we have? We have pressure energy, we have our kinetic energy, we have our potential energy. So this is what this hydraulic energy grade line does. It represents these energies in a form of in a graphical form, and what we are going to do first is to convert the terms in our Bernoulli equation, that is the pressure, that is our kinetic energy of rho v square, and that is our potential energy. So what we are going to do first is to convert each of these terms to length, and by doing so what we are going to do is to divide this by gamma, and by dividing this by gamma, the unit that what we are going to get for this term, for each term in this equation, will be in terms of length, and we can call these heads. We already discussed that what is a head. So by dividing the pressure by specific weight, what we are going to get is a pressure head. By dividing the kinetic energy with a specific weight term, we will get our velocity head, and what we are going to do is to divide the potential energy with the specific weight. So these two terms cancel out, and what we get is the elevation head. So first of all, we are going to represent our Bernoulli equation in terms of heads, and then we will see what the how the hydraulic grade line and energy grade line uses this head concept to represent all these energies in a flow. So the hydraulic grade line and energy grade line are graphical forms of Bernoulli equation. So how this is a graphical form of Bernoulli equation? This is our Bernoulli equation in terms of head. Now we have divided each term by our specific weight. So this is our pressure head, this is our velocity head, this is our elevation head, and this summation overall is equal to our total head. This is the total head. So by applying the conservation of energy term to this equation, we can say that our total head remains conserved. Okay, so if we are talking about in terms of heads, so in that case our total head will remain conserved. So the energy line is a line that represents the total head available to the fluid. So what is the total head? We will see that in a little while. And the hydraulic grade line represents the sum of the pressure head and elevation head. So if we take these two statements and apply this on the equation that we are seeing right now, so the energy grade line will be the sum of these three terms, that is the total available head. So if we sum up these three terms, what we will get our energy line. And if we multiply, add the terms that are the pressure head and the elevation head, so what we get is the hydraulic grade line. You can now relate these terms to the definition that we did for our Bernoulli equation. That Bernoulli equation is actually our equation of motion for fluid. So by changing the pressure and the potential energy of the fluid, we can change the velocity of the fluid. So this is what these lines are going to represent now, and now we can actually see visually or graphically that how that pressure change and potential energy change results in a change in velocity of a fluid. So if we have this diagram, if we take this diagram, and here as you can see, this is the total head, and this total head is equal to the sum of elevation head, the sum of pressure head, and the sum of our velocity head. So this total head, this represents the energy line. This dotted line is the energy line. and this is the total energy that is inside the fluid, in a flowing fluid. So to go through this scenario, there is a flow that is occurring. The fluid is flowing like this, and to see the total energy in this fluid, what we have done is we have installed a pitot tube. This is a pitot tube. This is the pitot tube. We have installed a pitot tube to see the total energy available inside this fluid, and the length of water here overall represents, if we take this as our datum, this is our datum. Okay, so from this datum up to this height h, we have our energy line. So this line, this dotted line represents our energy line. This represents the total energy that is inside the fluid. So as we move down, now what we have done is we have installed a piezometer tube. We have a piezometer tube here. A piezometer tube shows us the static pressure. So that static pressure will be equal to our, that is our pressure head plus the elevation head. So this is what this static pressure is equal to. So this line, this level shows us our hydraulic grade line. So as we move along this pipe, okay, as you can see, the pipe diameter is changing. So the pipe diameter is decreasing. So what should happen is the velocity of this pipe should increase and the pressure should decrease. So this is what is happening right now. As you can see, this was the magnitude of our velocity, or our velocity head, and this was the magnitude of our pressure head, and this was the magnitude of our elevation head. So here in this case, the pressure head is more than the velocity head. So as we move along this flow, you can see that the pipe diameter is changing. So due to this change in the pipe diameter, change in pressure will occur. The pressure will decrease. Now our pressure head is this much, and our velocity head has increased. So now you can see how the pressure head has converted into the velocity head. And if we come to this area here, now you can see that the pressure head has decreased even more, and our velocity head has increased. So you can see the change in pressure results in the change in velocity graphically now. And what this diagram represents is the graphical change in our pressure head and the graphical change that we are seeing in our velocity head. So again, this total will come out to be, if we want to see this, this is the total head, and this total head is equal to the velocity head, the pressure head, the elevation head. And this is what this diagram here is representing. And by changing the diameter of this pipe, we can change the pressure of the pipe, and by getting change in pressure, we can see the change in the velocity that is increasing as we move along this pipe. So here again, I want to point out that the pressure head is measured from the center of this flow. So if this is the center of this pipe, so this is from here we will measure our pressure head. So this is the point from which we measure a pressure head up to this point, the length of the fluid in the piezometer tube, and this is from the center of the pipe up to the height of the piezometer tube. So this will give us our pressure head. Below this, up to our datum, will be our elevation head, just like shown here, just like shown here. So this is what I wanted to show you, that actually the energy grade line and the hydraulic grade line are the graphical representation of Bernoulli equation, and the simple definition of Bernoulli equation is the change in pressure results in change in velocity, as we can see in this criteria that is given to us in the shape of this diagram. So we have seen that by changing the pipe diameter, the velocity of the fluid is changing, the pressure is decreasing, or as we define it in the form of heads. So the velocity head is increasing when the pressure head decreases due to the change in the cross section of this pipe diameter. So this is what we get. Our energy grade line is equal to sum of the pressure head, velocity head and the elevation head, and our hydraulic grade line is equal to the sum of our pressure head and the elevation head. As you can see here, this is our hydraulic grade line. This is our hydraulic grade line, and below this line what we are adding is the pressure head and the elevation head. Here again below this line we have a pressure head and our elevation head, and below here we have our pressure head and our elevation head. So to come to the final conclusion from this diagram is the change in velocity occurs due to these two heads, that is the pressure head and the elevation head. That is the pressure head, that is the elevation head, that is the pressure head, that is the elevation head. And that is what we defined earlier in our first slide, that the change in kinetic energy occurs due to the pressure energy and the potential energy inside the fluid, or the change in velocity head, because we have now introduced the term of head to this Bernoulli equation by dividing it by specific weight. What we got is the pressure head, velocity head and the elevation head. So the change in velocity head will occur when we change the pressure and the elevation head. As we can see graphically now, when we move along this flow, the change in velocity head occurs due to change in pressure and velocity, the elevation head. So this was basically the energy, and the hydraulic grade lines are basically graphical representation of our Bernoulli equation, and by subtracting hydraulic grade line from our energy grade line, what we will get is our velocity. In this case, this is the velocity head. So now let's see another example. So now we are going to see the example of this tank and again explain a little bit further our energy line and our hydraulic grade line. So what we are going to do is we are going to move from point to point, and we are going to write our different heads, that is the pressure head, velocity head and the elevation head. So first at point 1, the total head is equal to the elevation head, because at point 1 what we have is the velocity of the fluid is 0 and the pressure is atmospheric, so the pressure will also be 0. So overall the energy line, if we want to represent it right now at point 1, will be equal to Z1, that is equal to the total elevation head. So this is for point 1. Now let's move on to point 2. This is our point 2. This is our datum, just I forgot to mention it earlier. This is our datum from which we measure our elevation head. So this is the datum. This is the datum. So at point 2, now our fluid is flowing. Now our fluid is flowing and it has come down to the height of this. So what happened is some of this elevation head converted into pressure head and the velocity head. So this is how it is represented here, that at point 2, from the mean of this pipe, if this is the mean line, the center line of this pipe, so from this center line up to this level of water, this is the pressure head, this is the elevation head, and this is the head that got converted into velocity when this fluid start moving. And if now we look at point 3, if we take point 3, so at point 3 what's happening is the now the pressure change, the total pressure change has converted into the velocity, and our total energy line is equal to the velocity head and the elevation head. In this case the pressure change has occurred because the diameter of the pipe has changed. So by the change in this diameter of the pipe, what happened is this pressure this pressure head converted to the velocity head, or you can say that this pressure head, by the change in the diameter of the pipe, got added to this velocity head, and we got a new velocity head, that is for point 3. So at point 3, due to change in the diameter of the pipe, the pressure head got changed into the velocity head, and now at point 3 what we have for the total energy line is this velocity head plus this elevation head. So the addition of these two will give me my total energy line. So this is the graphical representation again of a Bernoulli equation, that how change in elevation, change in pressure, change in the velocity occurs, and how the change in elevation and change in pressure heads results in the change in the velocity of the fluid, and that is the velocity head, and that change in pressure head and elevation head results in the change in the velocity head of the fluid. So this was another example through which we represented these changes, and here again, as you can see, the hydraulic grade line is the sum of the pressure head plus the elevation head, and the energy grade line is equal to the sum of these three in this particular case. So this represents our total H, that is our total head, and this represents our hydraulic grade line, and this total represents our energy grade line, that is the total energy that was inside this fluid when this fluid was contained at a height h1, then it was flowed, then it was steady at point 2. At point 2, some of this Z, this elevation had got converted into pressure, and it came down to this level, and this amount of head got converted into velocity head. Now moving further down the pipe, when we moved further down the pipe at point 3, what happened is the pipe diameter changed. So due to the change in pipe diameter, decrease in pipe diameter, the pressure got decreased. So that decreased got added into this velocity head, and we got a new velocity head, and the elevation head here is Z3. So for here the energy grade line will be equal to these two heads, this head and this head, and here the energy line will be equal to the sum of these three heads, the velocity head, the pressure head, and the elevation head. And here for point 1, our total head will be equal to only elevation head. So you can see from point to point how these heads convert from one another, and how the energy is changing as the water flows. So hope this was clear. This was all done to explain the Bernoulli equation. What the Bernoulli equation is, the different type of pressures that we get from the Bernoulli equation, the static pressure, the dynamic pressure, and the total pressure, the flow rates that we measured, it was simple, and now the graphical concept of the Bernoulli equation, that is the hydraulic grade line and the energy grade line. So hope this was clear.